hello everyone. My name is RJ Crandall. I'm the Vulnerability Research and Reverse Engineering Team Lead at RII, Research Innovations Incorporated, but really known as RII. So we've been there at the booth and given out about 80 or so, maybe 80 to 90 badges. We still have a few more if anyone wants to grab any after this talk, but I want to run through the PIC16 solution, the reverse engineering portion specifically, and how it works. So introducing PIC, which has come up at least one more time than I expected today. It was made by Microchip Technology. There's a lot of variations. Most commonly you'll hear like PIC8, PIC16, PIC24. And there's often some confusion as these are grouped together into different families, baseline, mid-range, advanced. They also have some MCU ones, and those don't line up with those PIC numbers. So case in point, the PIC16 F54, which is the controller used here on this one, is a baseline, whereas the PIC16 F874 is a mid-range. So sometimes the numbers can be really similar, but don't necessarily reflect the capabilities of the device. So as we look at this, it is a Harvard architecture, and so as a separate bus for the instructions and the data, and it has a single register that we're working with, the W register or the working register. And so what is interesting is that each word in the instruction memory is 12 bits wide. So for every one increment in the instructions, we have 12 bits that we're actually accessing and decoding as the instructions. Whereas on the data side, they are 8 bits wide, and so we have a grand total of 19 available user addresses, so 19 bytes for all the data you want to do in your fantastic code to make these lights go blinky blink. And so a common problem is that people run out of space and things like that. So there's also these special function registers or SFRs, and those are what we see on the data side is like status and FSR, port A, port B. So intro into the instruction set, there's really only a few instructions available, surprise, surprise, and really even fewer that we need to understand. So we have a lot of our arithmetic ones, including add and, subtract, XOR, and we do all those. Move F will move the contents of one of those special function registers into W, whereas move WF will take contents of W, put it into one of those special function registers that you specify. We do have a call, we also have a goto, and return LW, which will also let you return a value from a subroutine in the W register. Tris A and Tris B stands for tri-state A, tri-state B. Essentially, these are the ways that you configure which pins are input and output, and all these pins available. So port A is 4 different pins on the outside, and then port B is 8 of the other ones. And so when we actually read or write to port A or port B, which is one of those special function registers, that's how we actually interact with the state of the pins. So the goto statement is also kind of the only option we have because branching is so limited. So we have bit test F, skip if clear, and bit test F, skip if set, which will look at one of those special function registers that you specify, or any of your general purpose registers as well, and then we'll either execute the next instruction or skip the next instruction, and that is it as far as where you get to branch to. So the conditional branching logic almost always has a goto right after it in that one spot because you're either going to execute it or you're not. So luckily Ghidra advertises support for PIC12, 16, 17, 18, and 24, but we learned a little bit about those baseline and mid-range and different family distinctions. And at least from my experience, it turns out that Ghidra seems to support the mid-range devices reasonably well when you pick the PIC16 assembler or disassembler. But the baseline PIC16 F54, which I'm interested in, is kind of mangled. So like we said, these 12-bit words are not interpreted in the right order, so really every instruction was wrong. The reset vector isn't at the right address, so you don't start looking at the right code. And many of those special function registers don't actually line up with our data sheet. So you could probably experiment, and there may be some other options in Ghidra, but I think it's more fun to write an architecture plugin anyway for Binja. So I'm a little biased, but as we look here, there's just a screenshot, and you'll see a nice, healthy dose of gotos. And so we're going to go to a little demo and explore what's in that just a little bit more. All right. Where are we at? Double click the header. Yeah. There we go. All right, so here's our reset vector, which, lucky in my little plugin here, gives you some helpful instructions because instead of actually making a goto, the XC8 compiler decided that, hey, I don't want to go to. We have enough of those. We're just going to roll over when I roll above the address limit. So if your code starts executing, then all it does is basically do this and then roll right over to address 0. And so as we look here, that's our main loop. So again, the go-to, compilers are fun. We clear a bunch of registers and go to this function here, which we can see is outside the main loop. We see a lot of loops and things happening right below us, and that's going to be our infinitely executing badge flashing pattern. So as we look through this, normally I would look and find where I'm trying to go, where's the destination, what actually impacts the secret code and the ability to flash the lights to a different pattern, like we told you is there. But instead we're just going to go top down for the sake of lightning talks. But as we look in here at this initialization function, we see those tri-state port A and port B. And compared to the code that was publicly available in the GitHub, you'll notice that instead of setting port A and port B both to zeros, we set port B to C0. And those 2 bits in C0 say that these 2 pins are input instead of output. Normally we set all the pins as output and makes it very clear that we're only using that as output. So as we go back there, we come into our main loop, and I've tried to add some comments that you can kind of read, but a few main things. And we start by seeing, what are the things that we can see on the badge? Where can we find our footing? And as you look in this, you'll see this function writes to port A and port B and writes all Fs to port A and port B, so that basically is our flashing pattern. And if we pay a little extra attention, kind of figure out the calling convention, which is not really specified or standardized because there's no real concept of a stack like we're used to. All your local variables are global variables really. But as we see this move 5 into general purpose register 2, and then we see DC and 5 here moving in. So what we're actually getting is we're going to flash 5 times, and each time is going to have an on-off duration of this number of ticks, which is just an infinite loop, or I should say a spin loop. And then we delay for a period of time. And here we see one of our most interesting things where we move from special function register port B into the W register, and then we move that W register into port 18. So we're caching that input and immediately doing a bit test on port 7. And if you look at port 7, you start to see what pin that is on the microcontroller, and it's one of either the data or the clock pin coming out. So if that is set, then we go here and do some additional logic where we now do a complement, do some bit math, but essentially we now do another comparison against the input, and we're going to bit test F, and then we're going to skip if it's clear. So essentially this is checking that one pin is set and that the other is not set. And if we reach that successfully, we move a value into GPR1. And we start building this pattern of moving from this temporary GPR1 into GPR13, which is saying, hey, I've gotten the secret code right thus far. And then we'll go through, and then we see a flash again, and one thing that's unique here is that we're moving 1 into GPR2. So the normal flashing pattern was 5 fast flashes, 3 slow flashes, 5 fast flashes. Tongue twister, I got it right. So what's interesting here is instead of assuming that, oh, I see the flash function, that's the first group of flashes. I see the second, this must be the second group of 3. This is actually just one individual flash in that group of 3. So then we're checking, and we kind of pull out that cached value from GPR13 and say, hey, if we didn't get the code right the first time, we're just going to bypass this check altogether. Else we're going to come down here and do a very familiar looking bit test skip of set. And this is the group of basic blocks here that look very good. So we continue down that branch and we see the exact same thing, although in this time we see a different pin being set. And so each badge was a little bit different, and I'll show that in just a second. But as we continue to come down here, eventually all those things add up and we store in GPR13. And at our final check here, we want to test and make sure that that was non-zero. And if it was, then we come down here, and this is the unique secret code pattern. So to help facilitate the input to the devices, so we've got the probably 2 bright flashes, 2 bright of LEDs. But when we come here, I have this handy device that all it does is light up some LEDs and make it a little bit easier to see your input. So there's the 3 slow flashes, and I just need to put the right inputs in at the right time. 2, 3, 4, 5. So I'm going to go input 1, input 2, input 3. at which point we get the secret pattern. All right. So if I want to go back to the demo, all right, let's see. Maybe. Good enough? All right. So what else? We do have a branch. So there's some intentional not lifting to LOIL because I thought that would be a little too explicit, maybe make things a little too easy, and really wanted to give you a chance to explore the PIC architecture if you haven't done that before. So we will probably publicize that soon. I also know some of the competitors did that as well as part of their solution trying to lift the architecture. And an interesting thing, this was an educational experience for the team in providing people opportunities to solder and assemble the badges, to design the circuitry, do the manufacturing process, and also just working with microcontrollers in a way that they might not have had a chance to do on their programs yet. So we plan to probably publish a blog post at some point when we get around to it about that experience and kind of lessons learned there. So the GitHub link is there. In case you don't have a badge, you're welcome to come grab a badge. We want to thank everyone for playing. We had 6 people or teams come solve that challenge. So thank you.